You've heard the phrase one step from disaster. In Goldsborough's case, that step was mechanical. A single dynamo-powered arm safe switch inside a hydrogen bomb. When the B-52 broke apart, the bomb's other arming sequences behaved exactly as designed, until that switch resisted just long enough to cut power to the firing system. We'll trace this part's engineering lineage and explain why its survival defined Cold War safety doctrine for decades to come. It began as an ordinary airborne alert mission, part of the Strategic Air Command's continuous readiness cycle in early 1961. These coverall flights kept nuclear-armed B-52s circling predetermined routes around the clock. Each bomber operated with full fuel tanks, 2 thermonuclear weapons, and a rotation schedule designed to put a credible deterrent force in the air at all times. The logic was straightforward. If a first strike disabled ground bases, the airborne fleet would still be ready to retaliate. By that winter, aircraft like the B-52G involved in the Goldsboro incident had already flown thousands of hours on these long-duration patrols. Crews adapted to a system where flight decks rarely went dark, and refueling rendezvous became as routine as taxiing. This operational intensity came at a structural cost. The B-52G's aluminum alloy wing spars and fuel cells, continuously flexed through refueling, vibration, and turbulence, accumulated fatigue that engineers could measure but not fully eliminate. The crews knew the pattern: 20-hour flights, aerial rendezvous over the Atlantic, and repeated pressurization cycles. On January 24th, the aircraft designated 58-0187 was returning to Seymour Johnson Air Force Base after one such patrol when a significant fuel leak began on its right inboard tank group. The loss shifted balance and created asymmetrical loading on a wing already taxed by strain. At roughly 9,000 feet, the airframe entered a flight regime it was never meant to sustain. Moments later, the right wing failed. The sudden loss of lift twisted the fuselage, snapping hydraulic lines and scattering sections of the tail. Major Walter Scott Tulloch ordered the crew to eject as control surfaces froze and warning lights illuminated across the board. Within seconds, the B-52 disintegrated. Fragments of fuselage tore free, and the bomber's internal racks released both Mark 39 thermonuclear bombs. 5 of the 8 crew members parachuted out successfully before centrifugal forces rendered further ejection impossible. 3 men never cleared the wreckage. The intent of such missions had always been to project readiness, yet this disintegration exposed the contradiction between deterrence and safety. Air Force records already showed that fatigue-related issues were increasing as total airborne alert hours rose past several million. The wing structures of some B-52 variants displayed early cracking patterns, prompting reinforcement programs that were still underway. The accident therefore reflected not a single oversight, but a systemic stress distributed across the fleet. As sections of the bomber fell, debris ignited scattered fuel, producing localized flashes across a 2-square-mile area of farmland near Goldsboro, North Carolina. Each major structural element followed its own trajectory. The vertical stabilizer landed inverted, parts of the fuselage came down burning, and 2 nuclear weapons descended along separate paths. One device's parachute system responded as intended. The other, released at a lower altitude, entered free fall. That split second created 2 entirely different experiments in real-world weapon safety. The aircraft's failure had concluded, but attention was now shifting from the destroyed airframe to the design of the weapons that survived the descent. Both bombs left the same aircraft within seconds, yet their paths could not have been more different. Released amid the breaking fuselage, one descended beneath a deployed parachute canopy, while the other fell unrestrained into open farmland. Those opposing fates revealed how a single mechanical distinction defined the line between a controlled descent and a near-nuclear accident. As the B-52 disintegrated, its internal bomb racks failed in sequence, releasing the aft weapon first at roughly 10,000 feet. That device, later cataloged as bomb number 1, separated cleanly and showed an orderly sequence of events. Separation lanyards pulled, drogue chutes unfurled, and the large 100-foot diameter main parachute blossomed within seconds. Each action provided enough drag and time for partial safing circuits to cycle as intended before impact. The forward position held bomb number 2, which left the wreckage at a far lower altitude, somewhere between 5 and 2,000 feet. The release sequence was incomplete, and its parachute pack never opened. Free of aerodynamic braking, it reached terminal velocity before striking soft ground, producing a crater roughly 5 feet deep and 9 across. From that moment, the investigation turned to what had occurred within each bomb's internal circuitry during descent. in bomb number. 1. The deceleration forces were moderate enough that the MC-722 arm/safe switch retained mechanical alignment. Its rotating drum remained set to safe, keeping the firing line isolated from the high-voltage generator. Despite the initiation of other arming steps, like the withdrawal of safety pins and sequencing relays engaging, the lack of continuity across that low-voltage contact line stopped the process short of the firing threshold. For bomb number 2, the outcome was less defined. Upon recovery, technicians found its indicator drum rotated to the arm position, a fact later checked against fracture patterns around the panel mount. However, the electrical internals had been torn apart by impact shock. The toothing between the indicator and its contact assembly sheared away, leaving the visual state out of sync with the circuitry. Metallic scoring showed where the contactor had momentarily bridged, but the relay path was broken and no charge could propagate. Current testing at Sandia years later would simulate this effect, showing that contact separation and loss of continuity at these velocities were plausible outcomes. Parker F. Jones summarized it candidly in his post-accident report, concluding that if bomb number 1 had simultaneously suffered inadvertent operation of its ready-safe switch prior to the breakup, a nuclear detonation would have resulted. The contrast owed partly to manufacturing tolerances. 2 nominally identical switches, but minute variations in seating torque and alignment created diverging stress responses under load. Where the parachute descent preserved mechanical order, the free-fall impact converted design confidence into uncertainty. One rested among tangled trees with its circuits mostly intact. The other lay fragmented in a smoldering crater. So, with the mechanical drama defined, attention now centered on the instrument that determined both weapons' outcomes, the low-voltage interlock buried within their arming assembly. Inside the recovered debris, most circuits were fractured beyond identification, yet one small electromechanical unit retained form, the MC-722 arm/safe switch. Within its dented housing sat a rotating drum that governed the transition from passive safety to active readiness. It required a 28-volt signal from the aircraft's wiring to unlock the firing chain. That modest current, driven by an internal dynamo, was the only link capable of allowing the bomb's high-voltage generator to operate. During the Goldsboro accident, that link never closed, and the absence of a few volts defined the difference between survivable impact and detonation of a 3.8 megaton device. The MC-722 and its later MC-1288 variant belonged to a family of kinetic interlocks used across multiple thermonuclear designs. Their purpose was isolation. So long as the switch remained on safe, the firing capacitors of the MC-788 high-voltage system were electrically stranded from any power source. Only when every environmental sequence, separation from the aircraft, parachute deployment, and arming rod extraction, completed correctly would the circuit energize. It was therefore a mechanical guardian that required an exact physical chain of events before the internal solenoid lifted its contact arm. The logic assumed that no uncontrolled or partial sequence could supply electricity to the explosive lens initiators. What made the Goldsboro case distinct was that nearly all those interlocks had already cycled. One bomb's parachute activated its timing motor and thermal battery. The other's free-fall impact had sheared its safing pins and triggered low-voltage systems by inertia. Yet the MC-722's contact spring never achieved electrical continuity. Post-recovery dissection showed no evidence of burn marks or solder transfer that would accompany current flow. The rotational drum had turned within its mount under far greater torque than design load, but the stop tab halted movement before the wiper blade crossed the conductive bridge. The bomb effectively remained open circuit while its other systems acted as though armed. Later, engineers at Sandia recreated this environment using accelerated shock tables. Components identical to those found in the Mark 39 were mounted and subjected to vibrational and impact forces matching the crash profile. The test data showed that the contact assembly could tolerate shock pulses above the rated limit without completing the circuit. Even with deformation of casing mounts, the MyCA insulation held off voltage up to breakdown. It was crude by modern standards, but reliable under mechanical abuse. This endurance explained why the weapon's firing capacitor bank, the X unit, never reached a charged state despite every other procedural step completing. That single unit thus served as the final practical barrier in a cascade of design redundancies. Modern flight control systems mirror this philosophy. Multiple independent safeguards exist, but a single correctly behaving component often prevents structural or energetic failure. In this instance, a few millimeters of separation inside a nickel-plated housing imposed an absolute boundary against runaway voltage. Its refusal to close under stress became the mechanical limit that kept one region of North Carolina intact. and its performance later guided revisions to nuclear safety architecture and to the termination of continuous airborne alert routines. A single low-voltage switch, never designed for heroics, proved that nuclear safety can rest on the ordinary physics of resistance, friction, and contact gap. One surviving component halted the 3.8 megaton firing chain through mechanical restraint, not theoretical precision. Parker F. Jones described it plainly. One simple dynamo technology, low-voltage switch, stood between the United States and a major catastrophe. That observation reframed safety engineering as a function of modest reliability rather than guaranteed perfection. The subsequent redesign, the MC1288 interlock, ensured future control circuits remained inert when marked safe. The Goldsboro switch remains proof that simplicity, correctly applied, can decide survival.